my screen.
Yeah.
And I'll start my talk here. Just a moment. Okay. Are you seeing any black boxes on the screen? If no, I can start.
Okay, it's clear.
It's clear. So, first of all, I would like to thank the organizers for giving an undergraduate like me, all the way from India, a chance. It's 2 a.m. right now in India, and if I just go off another direction or misspeak something in my conference, just blame it on not on sleep. So, I would like to start my conference by saying, "Hola a todos, los presenters para mí charla." That's the only Spanish I would try to speak in my talk. All the pleasantries done, we'll move forward to the title of my talk and the work done. So the title of my talk is a computational simulation of reaction networks involved in organic reactions. And the organic reactions we studied were formose and glucose and mylard and various others more that you will see in my talk. This work was done as a part of a summer research program with Blue Marble Institute of Science. You can check their Young Scientist program, it's very good. And my PI was Dr. Henderson Jim Cleaves from ELSI Japan, Tokyo Tech, and now he's moving to better options. So I'll begin my talk. Excuse me. Before starting on, I would like to explain the workflow of my project as I feel that the workflow is very important. So we study, as I mentioned, we studied alkaline degradation of glucose and formose reactions. Alkaline degradation of glucose can be seen in various stuff, like you can say in the browning of apples. Maillard can be seen when you cook stuff on your gas stoves and the amino acid degrades. So what we did, we applied rule-based reaction networks, 10 graph transformation rules. We took the outputs, applied various constraints. What are those constraints? I will be talking about in my few further slides. And then we add isomorphism tests to match our outputs, and then we finally check for the autocatalytic loops. The word autocatalytic loops is very important as this will form a basis of the main basis of my project. Moving on, what was the reaction-based, automated rule-based reaction mechanism I was talking about? So it was MOD, and it is developed by our collaborators, Dr. Jacob Anderson at University of Southern Vienna. What does it does? What is a reaction generation, and what is rules? What is all the graphs you are seeing? What are the nodes? I'll be talking about that. So coming on to this, origins of life always interested us, and I think it will interest all of the people attending this conference. Origins of life is one thing. So what we did, what we thought we will develop in silico based reaction mechanism generator so as to further unravel the secrets of prebiotic chemistry and search for autocatalytic loops. These autocatalytic loops can be further used in detecting biosignatures as a previous question was put up, phosphine one. So we hypothesized that these reaction networks can be used to detect glucose in say Martian environments or any other planetary environment. That's one thing. It can be used for drug metabolism and biosynthetic pathways. It can be used in origins of life, cheminformatics, chemical drugs. So it has a lot of options. So we are looking at how life originated from simple molecules combining each other, reacting with each other, and forming a lot of other molecules and forming life as we know it now. So we used an automatic rule-based generator, that is MOD. And the question we had in our mind, what if we had a software or a workflow that we input a set of molecules, input a set of reactions, it runs the reactions for us and generates a pretty graph, generates a pretty, you can say, workflow for us to enable us to find how the final molecule originated from the starting reactions. So that is it. And we use tautomers as starting molecules. Why? The question a lot of people ask me, why did you use only tautomers, and how did you generate those tautomers from the reactions? We used our reaction in the form of smile string, the basic smile string that are involved in alkaline degradation of glucose, formose, Maillard reaction. As you can know, glucose can take up various form of tautomers. So we generated the tautomers using Ambit and RDKit software, and then we cleaned up the tautomers. Why was cleaning needed? So we generated 3,000, 4,000, 5,000 tautomers, and it was getting computationally heavy. So we decided, okay, we'll clean up the tautomers and find out more stable, suitable structures that we can work on and make autocatalytic loops, those networks that you see, make the nodes, and further build upon them. So how did we select the most useful tautomer from the bunch? We used various techniques, various basic fundamental rules in organic chemistry to find out more stable structures, and we set up constraints that I was talking about in my workflow to figure out, okay, we need this kind of tautomers, we need these number of rings, we need these number of hydrogens uh, in our final structure, and this was accomplished by Ambit and RDKit software. As you can see on my screen, post filter generation. So here is a basic example of an unstable structures. We don't want these kind of structures in our output. These kind of structures actually populate our output very much more, so as to make our workflow computationally expensive. So unstable structures were forbidden. Carbons with two double bonds were forbidden. We set up a maximum molecular weight so that we know what molecules we are working on, and it helped generalize our workflow. And as I said in my workflow, we match isomorphism text data. So we use isomorphism text test to match the data for Formose reaction and glucose hydrolysis from a paper by Yang and Millis, Yang and Montgomery. Sorry for that, Yang and Montgomery. And this helps set us if we are going into the right direction or not, if our experiments are really working or not, if the data we are generating computationally really is matching with the data generated in the lab in the 1990s and early 2000s. So we matched a lot of data. It was really happy to see that a lot of data was matching, and the bridge between computational and wet lab research, the research that is done in lab and in silico test was really accomplished. And as I talked about what are rules, in life, rules are the set of directions that you follow to achieve something or to do something. So what we did, we used smiles for alkaline degradation of glucose and formose. We took those smiles, defined those rules. Rules are the basic organic chemical reactions that we have studied. For example, enol tautomerization and various kinds of other tautomerization. We took a bunch of 40, 50 of them. We applied those rules. We implemented those rules on our smile string, and we got the outputs. From the outputs, we filtered, we processed, we post-processed, and then we generated the graphs that you saw earlier and the graphs that you are seeing on my GIF for the mod software. Moving on to the main portion of my talk, autocatalytic loops and where to find them. That's a really cheeky title that I thought of. And first of all, what are autocatalytic loops and what is even autocatalysis, and like why did we really need autocatalysis? Autocatalysis can be defined as if you take a molecule A, you take a molecule B, you react them, and then you react those products with the reaction with the reactant itself, and then how the chain propagates. And as you can see on my screen, we used a graph-based database known as Neo4j to populate all these various kind of networks and autocatalytic loops. And so one of the main fundamental question about autocatalytic loops is SNA. And flux balance analysis. So we use stoichiometry, we use various kinds of stoichiometry network analysis and our networks to generate autocatalytic loops and to figure out what kind of pathways that we are needing and what kind of biosynthetic pathways that we need. We filtered the loops, we searched in the cycle all through Neo4j, and as you can see on my screen, we use stoichiometry information and pattern matching. One of the two with two various papers that we referenceable. So it's really a key fundamental idea, autocatalysis in biology as well as chemistry, and there is a bridge that exists between living biological systems and the cheminformatic systems. So autocatalysis really helps you define various kind of approaches, various kind of problems that you are solving, and interconnect them. Perfect. As I'm moving to the end of my talk, what is the future scope of this work and what could be done next? So we decided, okay, how do different reaction networks, reaction A running the whole reaction network or the reaction B running the whole reaction network will converge and merge, and how they will behave if they're mixed and match complete. Using machine learning techniques, we will definitely look forward to that. Stoichiometry and thermodynamic parameters like Gibbs free energy to determine what is the feasibility of our reactions running. And in silico data, the computational analysis can become really heavy, and we don't really have the time to do thermodynamic analysis in 3 or 4 months of your summer internship, and kinetic parameters to see which reactions are fast, which reactions are slow, which reactions affect the autocatalytic cycle, and those catalyses more and which affect the less, and more exploration. And there are different number of ways to uh, remove the unusable unstable structures. There are n number of ways to find out which pattern removes 99.9% of those structures to give us a better output is the key factor that we need to take maybe in the future. And as I end my talk, so if you have any questions or collaborations, my email is on my screen, and I would like to thank my PI, Dr. Jim Cleves, and my collaborator, Dr. Jacob Anderson, and all my wonderful research associate at Blue Marble Institute of Space Science, and all the future budding astrobiologists or planetary scientists. Please do check their Young Scientist program. I benefited a lot of them. So that's the end of my talk. And thank you.
Okay, thank you, Siddhant, for your talk. Now we're going to some questions. We have questions. Thank you.
Hi.
Hello.
Hi, Siddhant. This is Francisco Faul from Universidad del Atlántico. And we have some questions from our audience, and I would like to say, okay, the question is, at some point, these simulations can predict structures that generate amino acids or other building blocks for life?
Yes. So when I talk about uh, yeah, that's perfect. So when I talk about the computational part about computational generation of structures, it can work with amino acid, it can work with nucleotides as the fundamental building blocks of life. So what you input is the way the computational pathway will flow. If I input sugars, I know which kind of structures I am expecting or not. I can run the same way for RNA. I can run the same simulation for amino acids as well. But I need to know what kind of reactions I am running for. For example, for my summers, I took the Maillard reaction, I took the Formose reaction, I took the alkaline glucose reaction. So in Formose, there are some sugars involved and there are amino acids definitely involved, but I focus more on the sugar part. This can you just need to rewrite the rules for the amino acids. You just need to take in account their structure, their patterns, and this will all be the same, and this will work on that.
We have another question, and is, can scenarios of reactions be generated of environments of the primitive Earth or of other planets?
Okay, so just let me rephrase that I got your question correctly or not. It's asking about we can get the reactions from Earth as well as other environments. I'm getting that from your question. So yeah, it can definitely get, as I said earlier, whatever reaction conditions you provide, whatever conditions you input in the workflow, it will provide on that. So as I talked about biosignatures on Mars, if I take glucose as a biosignature, I'm not really saying there's glucose exists on Mars. But yes, if you take glucose as your mass, you can find out you can find out the basic fundamental structure in atmosphere as well as landforms in your Mars, feed that in our workflow, and then the outputs you can patch, filter, match the outputs, whatever outputs you are getting. So you can get. So this can work with prebiotic chemistry, how life originated. That's what we are doing. It can work with modern reactions that are running in your lab. So if you want to check a reaction in your lab, you can first run in silico automation computational model, and then you can figure out, okay, I'm getting this in my computational structure and computational workflow. Can I get this in my lab? For example, you can look at the Powner synthesis pathway of RNA. You can try to run it on that. So if you get the same if you get the same products as you would get in the lab, then the workflow is definitely working. It can work on atmosphere as my other co-interns did. It can work on line forms. It can work with current reactions as well as prebiotic reactions. But the point is, you cannot we haven't really taken into account the temperature, pH, ionization, and n number of potential variables that could have existed on Mars or that could have existed millions of years ago. Computationally modeling all of them in such a short time frame isn't really possible. Say temperature or pressure that varies, and you have to add a lot of background information, background workflow into our existing workflow. So this is a simple workflow that could predict a lot of reactions. But if you want to take into account pH, temperature, ionization, as is will be the case with amino acids, you ask, there is a lot of ionization happening, pi and pH. You have to work something or the other in that, but that will be difficult.
Okay, Siddhant, thank you very much for your talk. We're going to hear the next speaker.
Just before I leave, I want to thank all the people. It's 2 a.m. in India, so I'm just keeping up, and that's why if you found something missing in my talk, it's just the sleep going. But yeah, gracias all the people. Thank you for this wonderful event, and I hope everyone will get inspired, and do look up at Blue Marble Institute of Space Science Young Scientist Program. Apply next year, and you will get a wonderful opportunity to work on. And do let me know. Do contact me up if you want to know about astrobiology opportunities for undergraduates. Thank you.
Thank you for you.